Kinetics. Introduction to kinetics. Reactions only happen when particles collide successfully and frequently, so bonds are broken and reaction can happen. Activation energy is minimum amount of energy particles need to collide and start a reaction. Maxwell-Boltzmann distribution curve shows the energy of molecules of gas or liquid over a certain temperature. Particles gain energy through collisions. Properties of Maxwell-Boltzmann distribution curve. The x-axis is collision energy and y-axis is fraction of molecules with energy. Energy distribution curve needs to always go through origin because there's no particles with no energy. Get particles have low energy as collisions causes some particles to slow down. EMP is the most probable energy, which is at the peak. Mean energy is by the most probable energy and isn't at the peak. Area under the curve is total number of particles present. Distribution not symmetrical. Only little bit of molecules has greater energy than the activation energy. Energy distribution curve never meets the x-axis as there's no max energy for a molecule. Increasing temperature. As temperature increases, the distribution shifts, so more molecules have energy. At higher temperature, the EMP and mean energy shifts, so more molecules have higher energy, but number of molecules with those energies decreases. Area under the curve stays the same because total number of particles stay the same. Higher temperature means energy of particles increases. Particles collide more frequently and more when energy is greater than activation energy. More collisions result in reaction. Temperature increases. Mean graph shows significantly bigger proportion of particles have energy greater than activation energy, so frequency of successful collisions increases. Measuring reaction rate. Rate of reaction is the change in concentration of substance in unit time. When graph is plotted with time against concentration, the gradient of the curve is the rate of reaction. Initial rate is rate at the start where reaction is the fastest. Reaction rate calculated by drawing curve for concentration of reactants or products, then drawing a tangent to the curve and calculating gradient of tangent. For experiment between sodium thiosulfate and hydrochloric acid, so can measure reaction rate by doing 1 over time, and time is time taken for cross under reaction mixture to disappear because of cloudiness of sulfur being produced, and reaction is sodium thiosulfate and hydrochloric acid, which forms sulfur dioxide, sulfur, sodium chloride, and water. Approximate because it doesn't include concentration, and it's used because we make the assumption that sulfur produced is fixed and constant. Effect of increasing concentration and increasing pressure. Higher concentration and pressure, there are more particles per unit volume. So particles collide with greater frequency, and there's a higher frequency of effective collisions. Doubling concentration means double number of particles per unit volume, which equals double the frequency of effective collisions. Concentration increases, mean shape of energy distribution curve doesn't change, so most probable energy and mean energy still in same position. But curve does go higher and area under the curve will be more because there's more particles. More particles have energy greater than activation energy. Comparing rate curves. Different volumes of same initial concentration will have same initial rate if other conditions are the same, but will end at different amounts. Higher concentration / temperature / surface area, the faster rate, so steeper gradient. Need calculate or compare initial moles of reactants to find difference between finishing volumes. Increasing surface area. Increasing surface area causes successful collisions to happen more frequently between reactant particles, and this increases rate of reaction. Curve doesn't move. Effect of catalysts. Catalysts increase reaction rate without getting used up, and this is done by given alternative routes or mechanisms with lower activation energy. Comparison of activation energies for uncatalyzed reaction and for same reaction with catalyst. If activation energy is lower, so more particles will have energy greater than activation energy, so there will be higher frequency of effective collisions. Reaction is faster. Lower activation energy, more particles have energy greater than activation energy.